So we can imagine this disk with radius a plus a prime. So this has r is equal to a plus a prime. That is sweeping out an area sigma. So it's an imaginary disk that is centered at molecule A. So this disk moves with a relative velocity v, capital V, with respect to A prime. So we have an imaginary disk of radius A plus A prime centered at molecule A and moving with velocity v with respect to the molecule A prime. So capital V is the relative velocity of this imaginary disk. And you can see that the area that will be spanned by this imaginary disk will be, the area will be sigma, which is pi a plus a prime squared, or if you have identical molecules A and A prime colliding, sigma will be pi diameter squared, which is pi 4a squared. And this is called the total scattering cross section. So this area is called the total scattering cross section. Now, if you look at the volume that is being swept out by this imaginary disk, it's going to be equal to capital V bar times tau. That's the mean free time, remember, tau. So before a collision, successive collisions. So we're going to have the height of a cylinder, which is V bar times tau, and the base area, which will be sigma. So the volume swept by the imaginary disk will be equal to sigma V bar tau. So if we have n identical molecules per volume, so let's say we have n identical molecules per volume, we would have the volume swept by this imaginary disk, sigma V bar tau, multiplied by number of molecules per volume, equal to 1 in order to have a collision. So we have to make sure that you can see there's already a half of this molecule that is inside this volume. We have to make sure that at least half of the other molecule is also half of it or more that has to be inside this volume, so that we're going to have a collision for sure. So that's the condition. So that basically implies that the mean free time tau will be equal to 1 over n total scattering cross section times V bar. And at the same time we have the mean free path, which is the mean speed of molecules V bar, not the relative mean speed. It's V bar times tau. So we're going to see that the mean free path is equal to mean speed divided by mean relative speed multiplied by 1 over n sigma. Now, let's think about this relative velocity. So let's say that A moves with a velocity v, and let's say that A prime moves with velocity v prime. Then we will have the relative velocity capital V is v minus v prime. That's our Galilean transformation, basically. And if you look at the average value of v square, so I want to look at v square bar, this will be equal to v square bar plus v prime square bar minus twice the dot product between v and v prime bar. The dot product of v and v prime is going to be 0, because this is going to be equal to v bar times v prime bar times cosine theta bar, and cosine theta bar is 0, all angles equally likely. We have a random motion of molecules, so all angles are equally likely. So we can see that v square bar is v square bar plus v prime square bar. And now I'm going to neglect, because this is not a rigorous theory, we're going to neglect the difference between the average value of v square and v bar squared. So we're going to neglect this difference and make them equal. So basically we will say that the v bar squared is approximately lowercase v bar squared plus v prime bar squared. And since we assume that all molecules move with the same mean speed, for all identical molecules moving with the same mean speed, you can say that v bar is the same as v prime bar. So basically this allows us to write capital V bar squared as v bar squared plus v bar squared, so it will be equal to 2 v bar squared. Therefore the mean relative speed capital V bar is square root 2 times the mean speed of the molecules v bar. So we conclude that the mean free path should be equal to, or can be estimated as 1 over square root 2 n sigma. So n is the number density, number of molecules per volume, sigma is total scattering cross section, and instead of n, if we have an ideal gas, we can use the ideal gas law. So for an ideal gas we can write P bar V volume is equal to number of molecules Boltzmann constant times temperature, which is P bar N over V Boltzmann constant times temperature, which is number density Boltzmann constant times temperature. Therefore, the number density, number of molecules per volume, is the mean pressure divided by kT. So if we substitute this result here, we can see that the mean free path is kT, the thermal energy, divided by square root 2 mean pressure times the total scattering cross section. So basically this gives us a very good idea about what controls the mean free path. If we have a high temperature, we're going to have a large mean free path. If we have larger molecules, the total scattering cross section will increase, the mean free path will decrease. If we have high pressure, the mean free path will decrease according to this elementary theory. Now let's look at the typical values of the mean free path that comes out of this estimation. So let's take a look at typical values. Well, we can assume the temperature is 300 Kelvin, room temperature. The pressure is 1 atmosphere, which is 1.01 10 to 5 pascals. We have a molecule radius about 1 angstrom, 10 to minus 10 meters, which is 1 angstrom, 2 Bohr radii. The total scattering cross section sigma will be then pi times 2a squared for identical molecules, 4 pi a squared, which is 12 10 to minus 20, it's roughly 12 10 to minus 20 meters square. And then we can calculate the mean free path to be the value of kT is 1 over 40 electron volts at room temperature, 1 over 40 times 1.6 10 to minus 19 coulombs, so that's going to be in joules, divided by square root 2 mean pressure 1 times 10 to 5 pascals times the scattering cross section, total scattering cross section, 12 10 to minus 20. So we find that the mean free path is approximately 2 times 10 to minus 7 meters, or 2 times 10 to minus 5 centimeters. That's our estimated mean free path at room temperature. Now the mean speed v bar is roughly square root kT over m. How did we estimate this? Well, you can think of the equipartition theorem, for example. 1 over 2 m v square is 3 over 2 kT. So you can see that v square bar is proportional to kT over m, or v bar is proportional to square root kT over m, because we're neglecting v square bar is approximately the same as v bar squared, neglecting the difference between the two. So this gives us the dependence on temperature, kT over m. So we're going to have for helium, for example, for helium gas, the mass is 4 divided by Avogadro's number, 6.02 10 to 23 grams. This is going to give us, for the mean speed of helium at room temperature, 24.5 meters per second. The mean free time is mean free path divided by the mean speed, 2 times 10 to minus 7 meters divided by 24.5 meters per second. We find that for helium the mean free time should be of the order 8 times 10 to minus 9 seconds. So it's in the scale of nanoseconds. So basically this says that in 1 second we're going to have 10 to 9 collisions for one molecule, and the mean free path L is roughly 10 to minus 5 centimeters. This is much greater than the molecule diameter, which is 10 to minus 8 centimeters. So we find that indeed the average distance between the molecules is large compared to the size of the molecule. So the molecules can be treated as point-like particles as we assume in the elementary kinetic theory. Now, basically, we're going through an elementary kinetic theory of transport processes. It's describing a non-equilibrium situation. This is not a rigorous theory. We're looking at only dependencies on significant parameters. We're working with a dilute gas where the collisions are rare. Collision time is much less than the time between collisions. The collisions almost do not take any time. The probability of a collision of 3 or more molecules simultaneously is negligible. The average distance between molecules is much greater than the Broglie wavelength, so that it's a classical gas, and quantum mechanics only plays a role during collisions. The probability of not encountering a collision in a time interval t we call P of t. The mean time between collisions is the mean free time tau. The mean distance between successive collisions is the mean free path L. We're assuming all molecules move with the same average speed, a lowercase letter v bar. We're neglecting the v speed distribution so that the mean free path is v bar times tau. If you have two molecules that are going to collide, one has radius a, the other one has radius a prime. If the center to center distance is less than a plus a prime, then we have a scattering between these molecules. If it's greater, no scattering. And we can find out the condition, the threshold condition for scattering, if you have an imaginary disk of radius a plus a prime centered at a, moving with a relative velocity v with respect to a prime. The area that is spent by this radius a plus a prime is going to be the total scattering cross section. And if we have n identical molecules per volume number density, the volume swept by this imaginary disk, which is sigma times capital V bar times tau, the mean time between collisions, multiplied by n gives us 1 in order to have a collision. So if you have half of the molecule A prime that is inside this volume, but basically that is equivalent to saying, this condition is equivalent to saying B is equal to A plus A prime. So you have you're just going to have a collision between these molecules, so they will touch with this condition. And therefore we find that the mean free time is 1 over n sigma capital V bar. The mean free path is lowercase v bar times tau. So we find that the mean free path is the ratio mean speed divided by mean speed to the mean relative speed multiplied by 1 over n sigma. And we can estimate the value of the mean speed, and since all angles are equally likely and we neglect the difference between v square bar and v bar square, we can find that the estimate value of the mean relative speed is square root 2 times the mean speed v. So L is approximately 1 over square root 2 n sigma, and the number density for an ideal gas is P bar over KT using the ideal gas law. So the mean free path has the following dependencies. It's proportional to KT over P bar sigma. And for typical values, room temperature, atmospheric pressure, the mean free path appears to be 2 times 10 to minus 5 centimeters, assuming a molecule radius of 1 angstroms, 2 Bohr radii. The V bar we can estimate to be square root KT over M, or it's proportional to square root KT over M. And we can find out that for helium, for example, the V bar should be 24.5 meters per second. The mean free time is of the order of nanoseconds, and the mean free path, being 10 to minus 5 centimeters, is much greater than the radius of the molecule, which is 10 to minus 8 centimeters, which is in the order of 10 to minus 8 centimeters. So indeed, the average distance between the molecules is quite large.